Hello and welcome back to Math with Mrs. Becker. Today in College Algebra, we are going to finish section 2.6 by looking at some real-life examples that have asymptotes. The first example, a utility company burns coal to generate electricity. The cost C, which is in dollars, of removing P percentage of the smokestack pollutants is given by this rational function. So C, cost in dollars, is 80,000 times P, which is the percent of pollution you're removing, over 100 minus P. Now notice they give us a domain. P is the percentage. So they're telling us that it's possible to remove 0% of the pollution. It means that you're burning the coal and you're not doing anything about the pollution. Up to, but not including 100%. This is because it's virtually impossible to remove 100% of pollution. So we can remove 0 up to 100%. Use a graphing utility to graph this function. So what we're going to do is go ahead and look at Desmos. Things to remember as we are graphing a real-life scenario. Very often we will have to change the window, and it's important to remember that whatever the variable that they use within the problem, we always want to make sure that we enter that variable as an X in our graphing utility. So let's go ahead and do this. Our numerator is 80,000, and again, in the problem it's P because it's pollution percentage. On Desmos, we have to enter it as an X. Divided by, on the bottom, it's 100 minus, again, we need to use the variable X. Now this is what I was talking about. If I notice that's my graph, that doesn't tell me a darn thing. I have to change the window. To change the window, we hit the little tool. Now remember X, that is our pollution percentage. They told us our domain. They said we can go from 0 to 100. Now Y is the cost in dollars. Noticing that the problem has an 80,000 in it, it's kind of an indication that it's probably pretty spendy to remove pollution from the air. So I'm going to go cost, 0. We can't have a negative cost. I'm going to go up to like 100,000, you guys. Just see what happens. 1, 2, 3. Okay, so here's my curve. So what I can see is this is the percentage of pollution that's being removed. This is the cost. Notice that as we get closer to that 100, holy smokes, the cost is like way high. This is all that you really needed to do as far as the technology piece. They just wanted you to be able to graph it. Just little reminders like if you have a real life story problem, when you enter in the variable, you always want to use X, and making sure that you're comfortable with changing windows. So here's what that graph would look like. Okay, let's keep going. You are a member of a state legislature. Well, congratulations. That's a pretty important job. So anyway, you are a member of a state legislature and it's considering a law that would require utility companies to remove 90% of the pollutants from their smokestack emissions. The current law requires 85% removal. How much additional cost would the utility company incur as a result of the new law? Well, additional cost means we need to actually calculate two different things here. We need to figure out how much does it currently cost if you're removing 85% of the pollution, and then find out how much would it cost if they pass the new law. So we have to remove 90% of the pollution, and in order to find the additional cost, we'll have to subtract the two. Now here's one of the only times in math where you will not turn a percentage into a decimal, because here they said that P is a percentage, so we leave it in that format. So under the current law, we want to figure out the cost. The cost is 80,000 times P. P is the percentage of pollution that you're getting rid of. The current law is 85%. Over 100 minus P, which again is 85. Let's go ahead and calculate that. 80,000 times 85 is 6,800,000 divided by 100 minus 85 is 15. So here is your current cost. If I go ahead and divide it, remember this is money, so we're going to round to the hundredth. It's 453,333.15 0.33. This is how much the utility company currently has to pay to remove 85% of the pollution from their smokestack emissions, okay? That's a lot of money. So that's a huge thing to budget for. Well, now the state legislator's like, dude, we need to get more pollution out of the air. So they're considering a new law where you'd have to remove 90%. So new law, let's go ahead and see what the new cost would be. 80,000. Now you're removing 90%. Let's go ahead and calculate that. So if I have 80,000 times 90%, holy smokes, this is 7,200,000 divided by 100 minus 90 is 10. So when I go ahead and I divide by 10, all I'm doing is crossing off a 0. So it ends up being $720,000. So currently, if you were that utility company, this is your cost to get rid of pollution. If this new law passes, this is your new cost. Look at how much money you would have to figure out, okay, where are you going to get the difference? And that's what the question is saying. What is the additional cost? So I need to go ahead and subtract the two. So if I have $720,000, that's the new cost, minus the previous cost of $453,333.33. The new cost is $266,666.67. That's how much that bill would end up costing that utility company. Obviously, you know, we want pollution out of the air, so it's a good thing. But if you were the person running that company, they might be a little bit nervous right now figuring out, how am I going to make this much extra money? Okay, so real life example. The reason why there is an asymptote here. Let's go ahead and look at this. I cannot simplify on anything on top and bottom. So this means that I do have an asymptote, vertical asymptote, because nothing could be crossed off, at P equals 100%. And again, we said that it's virtually impossible to remove 100% of the pollution. So that's why that would be an asymptote. So if I go back and I look at this graph, if I go ahead and I zoom out, you'll notice here's my 100% right here. Okay, so I'm just going to point that out. Your graphic gets closer and closer and closer and closer to it, but it will never actually reach it because it's impossible. Oh, sorry about that. It's impossible to remove 100% of the pollution. So it is definitely an asymptote. It gets really close to it. Here's that 100. It gets close to it, but when you zoom in, you'll notice it doesn't actually touch it. Okay, here's another one. Let's say you are somebody with really sensitive skin and in the summer you get sunburnt a lot. There's actually a mathematical formula that tells you how long you can be outside and expect to basically not fry. Okay, that's what this next question is. For a person who has sensitive skin, the amount of time, T, and we're looking at hours, the person can be exposed to the sun with minimal burning. They're not saying that you're not going to burn. It's just going to be minimal. Can be modeled by this function. Okay, so we have a rational function. S is your sensor scale reading. Okay, so it basically tells you how intense the UVB rays are at that time. So S is, again, it's called the sensor scale reading, tells you the intensity of the UVB rays. And it's anything from 0, and you can't have 0, because even if it's cloudy outside, did you guys know you can still get sunburnt? That's why here we can't have a 0. Also, if you look at our function, that would be our vertical asymptote, because I cannot cross this off. So when I go to figure out my vertical asymptote, remember you use the denominator. This wouldn't be a whole because I can't cancel it. It would be a vertical asymptote at 0. And it goes up to and including 120. Use a graphing utility to graph the function. Again, just helping you be comfortable with graphing different things. I'm going to get rid of my last example here. Maybe. There we go. Okay, then I'm going to go ahead and reset my window because I'm not sure what's going to happen here. Let's go ahead and graph this. Just like our previous example, 0.37, I'm not going to put in an S. I have to put in an X plus 23.8, there's the numerator, divided by, again, our variable is S. In the problem, it's just because it's an application, we have to use a variable X. So here is the graph. Hey, this one I didn't have to change the window. But notice, okay, we're going 0 to 120. So I am only looking at the right half of the graph because of the domain. We're not looking at the left. Notice I do have that vertical asymptote at 0. It's getting really, really close to 0, and it jumps up to a positive infinity, and we said that that's what would happen. Again, they kind of indicated that with our domain. Notice, though, I also have a horizontal asymptote, and we'll talk about that in a little bit, but it's getting close and close and close to 0, but it never actually touches. So that is the part that they want us to go ahead for the graphing utility, just to make sure that you're comfortable changing the window, entering a real-life story so you can see a visual of what's going on. Okay, decimals. Let's go on and keep working. The Suncer scale is based on the level of intensity of UVB rays. Find the amounts of time a person with sensitive skin can be exposed to the sun with minimal burning if the Suncer scale reading is 10. So you guys, all we're doing is just filling this in. 0.37 S is a 10 plus 23.8 divided by 10. So this is if the Suncer scale reading is a 10. So let's figure out the top. 0.37 times 10 plus 23.8. I have 27.5 divided by 10. Remember, when you divide by 10, all that's really happening is you're moving that decimal one place. So we would have 2.75 hours. So if you're somebody with really sensitive skin, this is something that you may actually follow. If the Suncer scale says 10, you can be outside for about almost 3 hours and you would have minimal burning. Okay, but all of a sudden, if that Suncer scale is 25, your time in hours, 0.37 times 25 plus 23.8 divided by 25. Let's go ahead and calculate that. 0.37 times 25 plus 23.8. This time, the numerator is 33.05. If I go ahead and I divide that by 25, I get 1.322 hours. So notice that as the Suncer scale value goes up, you have to be outside a lesser amount of time if you basically don't want to get fried. What happens, because this can go all the way up, your Suncer scale can go all the way up to 120. What if you check and you're like, hey, should I go outside? I have really fair skin and I get burnt easy. And you check and the Suncer scale rating right now is 100. How long can you go outside? Let's calculate that. 0.37 times 100 plus 23.8. I have 60.8. Divided by S, which in this case is 100. So if I divide it by 100, it's 0.608 hours. So a little bit more than a half hour, and you better get your butt back inside the house. Okay, so again, just being able to understand real life scenarios where the function is a fraction. It's a rational number. If the model were valid for all values, S is greater than 0. What would be the horizontal asymptote? So what you'll notice is I did go ahead and I kind of jumped the gun a little bit. I showed you this. So we're looking here. They're saying, well, what happens if you keep going? More and more and more and more and more. There is definitely a horizontal asymptote. As I go all the way to the right, it is approaching, but it's never touching the 0. 0 is the Y value. When I'm looking at this, the Y value is time. So the horizontal asymptote would be, we would have Y equals 0. Remember, it's horizontal, so it cuts the Y-axis. That's why the equation is Y equals. What does it represent? Well, in our case, the Y is t, which is time. The reason why it's 0 is because you can't tell somebody that you can go outside 0 minutes without getting fried. I mean, you can definitely go out a minute or two, even if the sun is really, really hot. So the time would never equal 0. Even if the Suncer scale was 120, you could go out for at least a minute or two. It will never hit a point where they're like, hey, you need to hide in the closet and eat sunscreen. Those of you who have ever watched Benchwarmers, you're laughing right now because you know what I'm talking about. The time would never be 0. You could always go outside at least and soak up some of that vitamin D. Again, that is the end of 2.6. There are a few questions in the book if you would like to try some more, or if, let's just say that this was kind of difficult for you. 39, 40, and 43 were pretty good questions just to kind of help your understanding. If this made sense to you, rock on, and we will move on to the next section. Talk to you soon.